Chapter 3, Designs and Serious Harms. In the previous chapter, we discussed what constitutes an accident. In Chapter 3, we want to talk about how designs can cause very serious harm. So at the end of Chapter 2, we noted that when we remove operator error and when we remove circumstances, what we're left is the design, the artifact itself, whatever it is we happen to be talking about. And in Chapter 3, what we want to do is look at a case where a design can cause extremely serious harms. Now, the case that all of you should be familiar with is the one from the reading, the Flight 965 case. Now, in many ways, the Flight 965 case is a paradigmatic case of bad design. Now, for many, it's the tragedy of Flight 965 is often attributed to pilot error. That it was the pilots that screwed up in some way during the flight which caused the plane to crash. Now, for a quick recap before we watch a video, which will be coming up in a moment, I'm going to show you an 8 or 9 minute clip from a documentary on this particular case, just to go over the main features. So if you remember from the reading, Flight 965 was going into Cali, which is in Colombia. They were typing into their navigation computer the Razo beacon. So as the plane comes in to check its location, to make sure it's going in the right direction, there are various beacons that are placed throughout the world. But in this case, the beacon named Razo, with an R, was the next beacon that they were to sort of ping from the plane. The pilot typed in the letter R. Now, it turns out that in this one unique case, normally what happens with a beacon is the minute you type in the name of the beacon or the first letter or two of the beacon's name, the closest beacon to the plane will show up with that letter. So as the pilots were very near the Razo beacon, when they typed in R, the Razo beacon should have shown up. What happened in this particular instance is that in this specific case, the computer was programmed differently. That when you type in R, no matter where you happen to be typing in, the closest beacon won't be the one that appears on your screen. It turns out that Bogota beacon, Romeo, will appear on the screen. So for some reason, through a quirk of programming or something that was chosen for some other supposedly practical reason, the letter R, when it brings up the list of beacons in order of the closest to the furthest away, no matter how close you are to Romeo, when you type R, the Romeo beacon is going to come up. So this is the sort of setup. The pilot types in the R. R should be the closest beacon because it's the Razo beacon, which they already knew the name of. So when they typed in R, enter, and they were on their way. Now I want you to note that as we watch in the video, which is coming up, this is a section of video, a clip obtained from the National Geographic channel. The title of the program was Crash on the Mountain. In this particular video, at about 8 minutes into the video, you'll notice that in this presentation of the crash, they tend to gloss over the computer issue. So in other words, they say the pilots looked up which beacon. Okay, it's the Razo beacon. They type in the R, they hit enter. And even in the video, it says that normally when you type in the letter or the name of a beacon, the closest beacon to you appears first on the list of available beacons. And they seem to let that information out, but then simply ignore it and move on. So I want you to watch the video. When we come back, we're going to talk a little bit about what we saw in there and to show how this acts as a sort of paradigmatic example of bad design.
This is your captain speaking.
We have begun our descent for landing at Cali. It's a lovely evening.
As we'd expected. We'll pass a shower or two on the way in.
This lovely evening is about to end. In 30 seconds, the pilots will make the first of a series of mistakes, which will result in the death of nearly everyone on board. American Airlines Flight 965 is on its final descent, roughly 100 kilometers from Cali. Cali's Aragon Airport is situated at the end of a long valley. On both sides of the valley are towering mountain ranges that stretch to almost 4,300 meters. It's a formidable sight.
One of these nuts done?
No, thank you.
You want your water? You want to wait until we get on the ground about your water?
No, I'll wait for the ground.
To guide the plane on its proper pre-programmed flight path, the aircraft must pass over a series of waypoints. These are generally radio beacons at fixed positions along the route. The plane's computer picks up the signal from these beacons, one after the other, and guides it safely to the destination. Flight 965 is now approaching the waypoint called Tulua. Tulua is a radio beacon at the head of the valley which leads to Cali. After passing Tulua, they should fly down the valley and pass over the final waypoint called Rosso. Then they fly past the airport, turn right, and land from the south.
She did really well.
È molto interessante. È molto interessante, sì.
Cali approach, American 965.
American 965, good evening. Go ahead.
Buenas noches, senor. American 965.
Cali Air Traffic Controller Nelson Rivera will oversee the final approach of Flight 965. But he has a problem. Insurgents opposed to the Colombian government have blown up the radar installation. Rivera has no way of knowing where planes are until they radio their position.
The distance, DME from Cali?
Without radar, the air traffic controller must rely on the flight crew to provide the aircraft's distance to the runway.
The DME is 6'3".
The DME is the distance measuring equipment in the Boeing cockpit.
Roger. American 965 is clear to Cali.
Descend and maintain 5,000 feet. Altimeter?
3002. Report Tulua.
Okay, understood. Clear direct to Cali, VOR, report Tulua.
Affirmative.
It's a misunderstanding. Captain Tafuri thinks he's being told to fly direct to Cali and forget all about Tulua. But the controller needs him to report when he passes Tulua so that he knows where the plane is.
To me, the word directly means that he was authorized to go directly to Cali, that there was no delay. Therefore, he had to inform us of his position in Tulua, because we don't have radar. I needed him to inform me of that exact location.
Tafuri punches direct to Cali in his computer. Since the plane no longer has to pass over them, all the waypoints between his present position and Cali will now be erased, including Tulua, the one he's now approaching.
Put direct Cali for you in there.
Okay, thank you.
Flight attendants, please prepare for landing. Thank you.
And I remember they gave us the order to put the back of the seat straight. I remember that. And everybody was so happy because we were very close to the city.
Five.
11 minutes before their estimated time of arrival.
965, go ahead, please.
Sir, the wind is calm.
Air traffic control asks the flight crew if they'd like to land on runway 19,
You want to shoot the 19 straight in?
instead of their planned approach to runway 01.
Yeah, we'll have to scramble to get down. We can do it.
Yes, sir. We'll
Need a lower altitude right away, though.
Roger. The American 965 is cleared to VOR DME.
Okay.
The pilots are pleased. Runway 19 is a straight-in approach from the north. They won't have to lose precious time by circling the airport. But there isn't much time. They need to start getting the plane down quickly. Williams deploys the speed brakes. The brakes are flaps on the top of the wings. When they're raised, they reduce lift and increase the plane's rate of descent.
Approach runway 19.
Rosso number 1 arrival. Report.
This split-second decision to land on runway 19 sets off a chain of events that will end in disaster.
Arrival will report VOR. Thank you, sir.
Report Tulua, VOR.
Report to Lua.
I gotta give you a Tulua first of all. You want to go right to Cal or to Tulua?
I thought he said the Rosso 1 arrival.
Yeah, he did. We got time to pull that out.
Events begin to unravel very quickly in the cockpit. The pilots have to locate the new charts for the approach to 19, enter the new route into the computer, and still fly the plane.
And Tulua 1 Rosso. Yeah, there it is. See, that comes off Tulua.
They're getting totally confused. The controller keeps asking them to report when they've passed Tulua. But having erased it from their computer, they have no idea where it is. Captain Tafuri asks the tower if they can forget Tulua and fly directly to Rosso, their last waypoint before the runway.
Can American Airlines 965 go direct to Rosso?
And then do the Rosso arrival, sir.
Affirmative. Take the Rosso 1 and runway 19. The wind is calm.
All right, Rosso, the Rosso 1219. Thank you, American 965.
Report Tulua at 21 miles and 5,000 feet.
Okay, report. Tulua.
The controller is still asking them to report passing the Tulua beacon. Without radar, he doesn't realize that they're already past it and are speeding down the valley towards the airport. Captain Tafuri now makes another fateful decision. Having decided that they're going to head for the Rosso waypoint instead, he punches R into his computer. The computer database responds by offering a list of more than 10 waypoints to choose from, all beginning with R. Normally, the nearest one, Rosso, would be at the top of the list, but tonight it's not. Captain Tafuri doesn't notice and pushes the execute button. At nearly 520 kilometers per hour and descending at a rate of nearly 400 meters per minute, Flight 965 begins to veer off on a new and deadly course.
I never imagined that they were deflecting the route in addition to losing altitude. Because I didn't have radar.
In the cockpit of Flight 965, the pilots are completely unaware of what they've done. They're busy studying charts as their plane crosses the mountains into unknown territory. For more than a minute, American Airlines Flight 965 has been turning off its proper course and into the mountains. Captain Tafuri and First Officer Williams suddenly notice that their aircraft is taking them somewhere that they don't want to go.
Let's go right to Tulua, first of all, okay?
Yeah, where are we headed?
17.7.
Captain Tafuri is floundering in the pitch darkness. If he could only find the Tulua waypoint, he could get his bearings. He switches from one computer system to another and then manually enters the radio frequency for the Tulua beacon.
Okay, I'm getting it. 17.7 just doesn't seem right on mine. I don't know why.
Left turn. So you want a left turn back around to ULQ?
No, hell no. Let's press on to...
Press on to where, though?
Tulua.
Hopelessly lost, and less than 2 minutes from impact, Tafuri decides to press on with his doomed approach.
Let's go to Cali, first of all, okay? We had here, didn't we?
Yeah.
Go direct CLO. How do we get here? Come to the right now. Come to the right now.
The pilots don't know it, but when the plane veered off course, it crossed over the mountains. They're now in another valley, parallel with the one they should be flying down. Passengers are completely unaware that in less than 60 seconds, the aircraft traveling over 340 kilometers per hour is going to crash.
We're almost there.
It's that Tulua I'm not getting for some reason. See, I can't... Okay, now. No. Tulua's
Okay, yeah.
but I can put it in the box if
I
you
don't
want
want to lose. Let's just go to the extended center line of
Which is Roseau.
Roseau.
Well, why don't you just go direct to Roseau then, all right?
Okay, let's...
I'm going to put that over to you.
They decide to give up on Tallulah and make straight for the airport. They don't realize that there's now a wall of mountains between them and Cali.
965 altitude.
965.
9,000 feet.
Roger.
Distance now?
The plane's ground proximity warning system is telling them they're about to crash.
965, this is Cali approach. Can you hear me?
Y ya no me contestó.
He didn't answer.
No me volvió a contestar.
He never answered again.
Easy does it. Easy does it.
I could feel that we were just violently just going up. And I felt like I was in a roller coaster ride or something.
Terrain.
Easy does it. Easy does it. Up, baby.
Instinctively, I reached over and I grabbed my father's hand and I put my head in my lap. In my mind, I just kept on thinking, come on, just straighten it out, straighten it out.
Up, baby. More. Up.
These were the last words on the cockpit voice recorder.
So having viewed the video, we can ask the question, what was the cause of the crash of Flight 965? Now, as I've already mentioned, it's often attributed to operator error. That is, the pilots made a mistake. Had the pilots looked at the navigation computer correctly, had they typed more than R in for the Roseau beacon, or they double checked what was on the top of the list, then this accident, this crash could have been avoided. But as the reading notes, it seems that a better way to view this is as a design that provoked error or provoked operator error. Now, how could it have been operator error? If we want to look at this case again, as most people still viewing this as operator error, what kind of error would it be? So there's one possibility, is that the pilot typed a T instead of an R into the computer. So the pilot actually typed the wrong letter for the name of the beacon. Now, as we saw in the video, in the recreation in the video, the pilot looked up the beacon. The pilot was aware of the fact that it was the Roseau beacon, which was linked to Cali, where the airline was going, or the airplane was going, that was their destination. So it's clear he didn't type in T or O or some other letter instead of R. He had actually typed in the correct letter of the name of the beacon. Now, under normal circumstances and everyday circumstances, the closest beacon, the one that they were closest to, would have been the Roseau beacon, and that would have shown up. So if they were heading into Cleveland and he typed a C and the name of the Cleveland beacon was Cleveland, then that would have been the one that showed up, not Pittsburgh or somewhere else. So clearly that's not the case in which it was operator error. He could have gotten the name of the beacon wrong. So in the one case, he could have just typed some other letter in. In this one, he could have just been mistaken. Maybe he checked the manual, maybe he misread, he didn't know the name of the beacon, or he just got the name of the beacon wrong. Well, it's clearly in this case, he didn't get the name of the beacon wrong. So it's not his error. He did look it up. They were going towards what they thought was the correct beacon, the Roseau beacon. And finally, it's possible that he intentionally typed an R and that he wanted to go to the wrong location. That he knew the R actually was for Romeo, or that Romeo would come up, so he knew that the R was the beginning of both names of both beacons, but he actually knew that the Romeo beacon would come up and that he wanted to crash the plane. It's clearly the case that that doesn't apply here either. This wasn't some sort of suicide on the part of the pilot of the aircraft. Now, what we see in this sort of design, it's really a design of the flight guidance system, is that there were a number of predictable problems. So you don't actually have to be a genius to see that there might be some things that could happen in a plane by using a system that has this exception to the rule. So to go back a moment, the exception to the rule is, in every other case, if you type the letter of the beacon, the first letter in the name of a beacon, the closest beacon with that name will pop up. In this case, there's an exception for the Cali and Bogota beacons. So if you're anywhere near, if you type in R, it's automatically going to give you Bogota and the Romeo beacon instead of the one that you're closest to. So we can see that the design of the program itself resulted in a foreseeable problem. Seems pretty clear that if in every other instance of a program, by typing a certain command, I get a certain outcome, this one exception one could foresee might cause error, that this might cause some confusion for the person using the program. It's also the case that we know that pilot distraction and stress is a known issue. So you could see in the video that the pilots themselves were becoming a bit stressed. They were attempting to land, it was dark, they were looking for the right beacon. The ground control in this case had a problem with radar, so they couldn't help them in that way. So we know that if we're designing a system, a navigation system for an airplane, that some of the things that happen when you're flying a plane are that there might be distractions or stress. So this is a known issue. This isn't a secret. It's not something someone wouldn't know who works in avionics. It's also the case that I think that pilots familiar with the program could make the same mistake. So as the reading notes, you don't have to be inexperienced. You don't have to be poorly trained. Even an experienced pilot may make this kind of mistake. Right? So there are things that we do all the time. There are exceptions to rules all the time. So, for instance, walking into a door that we think should open one way or another. We might say, in every day of my life, the door opens from the right, but in this particular building, it's on the left. And we could say that, look, even though I'm well aware of this, it still can slip my mind. So how do we guard against this kind of error? How can we guard against error in our design in general? Well, there are a few things. We could install some sort of warning device or warning devices. So taking Flight 965 in as example, it's possible you could say, well, whenever you type in R, there's some sort of red light to warn you that R is an exception to the rule. And in fact, we can do this. We do this all the time with various things. There are poorly designed things, and sometimes not even poorly designed things, in which there's some sort of warning. There are labels and diagrams and things. You go on a ladder and it tells you what you can put it, and don't put your aluminum ladder on electrical lines if you're trying to climb something. One would think this is obvious, but we have all these sort of warning devices on things, even things that are well designed. You can have a perfectly designed ladder, and yet there's still some sort of warning on there about where you should and shouldn't put it. We could simply, of course, redesign the artifact. And it seems in the case of Flight 965, this would have been the better alternative. So the reading notes that there are things you could have guarded against error on the computer. You could have put tape over certain letters. You could have a little piece of paper or a warning above the computer that says, if you're typing in R, note that you will be sent to Bogota and not the closest beacon. So there are other things we could have done warning-wise, but it's probably in this case one in which a simple redesign would have been the better alternative. What is evident from the case of Flight 965 is that we simply have a badly designed artifact. So we could put warnings, we could put tape or messages or something else to warn the pilots in cases where they're entering the letter R. But I think at the end of the day, it's just simply a badly designed artifact. Now there's two possibilities when we're talking about the engineer who did the design work on this particular program. The first possibility is that the software programmer chose this design. This was the chosen design of the navigation system. So it's possible that the programmer made an intentional choice whenever R comes in, because Bogota is the most popular place for planes to go. I think that R should always put Bogota at the top of the list. That's clearly where everybody wants to go. But let's say that's not the case. So it's possible that that's the case, that it was the chosen design. It was meant to do this for some reason. We could speculate why, but let's assume for a minute it simply is. But there's a second possibility. And it's possible that the flaw was not caught. So when the program was designed, for whatever reason, whatever went on under the hood inside this program, it just simply wasn't caught. And therefore was left in there, and that's what we have. So it was in some sense unintentional. What's interesting though, and as we'll see, or we'll see later in the course, it doesn't actually matter whether the engineer chose this particular design, that is from a moral point of view, it doesn't matter, or whether it was simply a case in which the flaw was not caught. In either instance, whether it's either of those two, the engineer is still at fault. It's still the engineer's responsibility. And so what we find here, and we haven't really made an argument for this yet, it's simply to note, is that moral responsibility does not depend on intent. And there'll be reasons why this is the case. So if you doubt this now, if you're still thinking, wait, that can't be right, the engineer would have had to have wanted to make this kind of error, would have intentionally done this, put this in the program for them to be responsible. Well, as we saw, there are accidents. Accidents can come from design, and they might say, well, okay, the artifact caused the accident, but couldn't it have been an accidental element of the design? And it's true, it might not have been intentional. It might have been a simple flaw that wasn't caught. But as we're going to argue, as a professional and as an engineer, and we're talking specifically about engineering, that does not relieve you of your moral responsibility. You can intend, or you can lack the intent to do any harm, and yet still be morally accountable for the harm. And that's what we'll talk about as we move on now in the course.